sir. So for till now, 40 people have joined, so we can start now. So, good evening, everyone. Myself Vishwajit Dev from Department of Physics, Assam University. I welcome you back to the third session of Day 4 of the International Year of Quantum Technology. Now we will hear from Professor Archan Mazumdar, a renowned figure in quantum foundation and cosmology, who will speak on quantum computing and information processing. Professor Mazumdar is affiliated with the S.N. Bose National Center for Basic Sciences, Kolkata, and holds both an MSc and PhD in physics from the University of Delhi. With over 100 publications in leading journals, his research spans quantum information theory, quantum correlation, non-locality, and cosmology. His significant contributions include advances in Einstein-Podolsky-Rosen steering, entropic uncertainty relations, and quantum teleportation, deepening our understanding of the fundamental nature of quantum mechanics. Beyond quantum theory, he explores primordial black holes, gravitational waves, and dark energy. An accomplished educator and communicator, Professor Mazumdar has mentored numerous PhD students and organized multiple international conferences. Let's extend a warm welcome to Professor Archan Mazumdar. Over to Professor Mazumdar.
Thank you very much, Dr. Deb. So let me begin sharing my presentation in slideshow. So let us say, so is my slide visible?
Yes, Professor.
Yes, sir.
Okay, slides are changing also.
Yes.
Okay, good. So now let me formally start this talk. And to begin with, let me thank the organizers for actually organizing this very nice workshop and school. and I hope it has been beneficial for the first few days to a lot of people who have attended. So today I will be talking of something which is, of course, related to quantum computing, and in a bigger sense, not only quantum computing but also to various other quantum information processing tasks. Well, quantum computing is one possible quantum information processing task, and due to the mixed nature of the audience, I thought I would make the ambit of this talk slightly wider, not just focus on quantum computing, but to include other information processing tasks also. And I will come to what I mean just in a few slides. And the title is Resources for Quantum Computing and Quantum Information Processing. And as I was introduced, I belong to the SN Bose National Center for Basic Sciences, Kolkata. And we have been pursuing this work, this line of studies in quantum foundations and quantum information from almost for the last 30 years. And we started from the basic science principles, and today these ideas are very relevant for technology. Okay, so how did it all come about? So, what is the current perspective on computing and information processing science? Well, first of all, since 1980s, in the last 2 decades of the previous century, first applications of quantum resources were seen in quantum computing and information theoretic protocols. So, previous to that, all these things like computing and any other information processing were done using classical laws of physics. And what was the difference? So, since 1980s, scientists realized that one could perform tasks using the superposition and entanglement principle in quantum mechanics, and such tasks were regarded as impossible using laws of classical physics. For example, in classical mechanics, you do not have any superposition, and similarly, in classical mechanics, you have no concept of entanglement. So, what are these possible tasks that one could do using such resources? In this case, by resources, I mean that some physical components of this theory, quantum theory, like superposition and entanglement. And these tasks, such as computing, quantum teleportation, quantum cryptography, etc., were first realized that these were possible using quantum mechanical laws since 1980s. Now, to begin with, of course, everybody has heard about quantum computing, and it is believed that the next generation of computing devices will use quantum computing principle. And already, when I say next generation, there are already prototypes for quantum computers available in labs around the world, and all of you have heard of these Google and IBM quantum computers. So, basically, what is a quantum computer? So quantum computer, by the way, I'm just giving you a brief, a survey of this thing. I mean, brief summary. Since before me, Professor Pankaj Agarwal has also talked in this workshop and is given you an idea. So I will be quite quick regarding the basic summary. So a quantum computer, for instance, uses quantum mechanical phenomena, as I just said, like quantum superposition and entanglement or entanglement to perform operations on data through devices, and these resources or these principles or phenomena are, as I said, superposition and or entanglement. In contrast, a classical computer, what does it use? It uses voltage which flows through circuits and gates, and the processes which happen inside a classical computer can be calculated entirely using laws of classical mechanics. So what is the difference? So for example, classical computers use the language of classical bits, and in classical bits there are two basic states which we can regard as on and off, or particularly typically using such voltages, and these can be labeled as 0 and 1. Note that they are mutually exclusive. Whereas in quantum computing, you use not just classical bits but qubits. So, how are qubits constructed? They are constructed from two basic states, which are states in quantum mechanics, like the ket0 state and ket1 state. So, I have written for you an arbitrary pure state in quantum mechanics using a superposition of these two bits, 0 and 1. Note the basic difference is the superposition, right? So A and B can take infinitely possible values, okay, real or complex. However, they are usually normalized. So what principle are we using here? We are using the principle of superposition, which is discrete in nature. So again, we can also go beyond it and use quantum entanglement, which tells us that two or more objects must be described in reference to one another, not individually. And an entanglement is, of course, a property which allows for non-local correlation. So we will come to that later. So again, why do we study quantum computer? Because in the last 3-4 decades, it has been realized that there are particular kind of simulations which can be done only using quantum computers, which help us to solve enormous amount of problems in physics, chemistry, material science, nanotechnology and other technologies, even biology and medicine. Okay. So for instance, a quantum computer can store and compute a large number of variables at once using the principle of superposition. And however, I mean, since these quantum mechanical simulations also have some process, they can be, although in principle you can do anything, but in practice they are indeed slow. There is another big need, I would say, of using quantum computers now, because all these secret keys in the whole world, like secret communication, password, etc., is can be cracked using quantum computers. So there is no way out of quantum computing. Okay, so this slideshow has again gone. So let me go back to this slideshow. So, okay, so let us now just do a recap of the basic differences between classical and quantum computation. So once we go from classical to quantum, bits are replaced by qubits, and the usual logic gates that you use in classical computing, like for example AND gates, OR gates, NOT gates, are replaced by quantum gates. Now in quantum mechanics, processes are unitary. That is the beauty of quantum mechanics, and so we have to use unitary quantum gates. And instead of classical circuits, you have quantum circuits. Now, the final stage of any computing program is trying to read the output bit and try to make sense from what kind of algorithm you have used. Now, when you're doing quantum computing, so because you are using quantum states, so you have to use the final state, and that can be done only by making measurements. Now, measurement in quantum theory, and I think all of you have studied quantum theory, measurement is quantum theory is a very, very, I mean, special phenomena, and there are certain rules for making such measurements. And what are the outcomes of measurements are also dictated by these rules. So you have to keep this thing in mind as well. Now, this is regarding quantum computation as a sort of summary. But what I was trying to tell you just from the initial slides, the ambit of today's talk is not just limited to quantum computation, but it uses other kinds of quantum processes or quantum operations and quantum phenomena as well, quantum algorithms. So let us typically try to see what other examples of these quantum tasks are, quantum information processing tasks. One example is again quantum teleportation, which is a beautiful quantum information processing task. And this has to do with the purpose of quantum teleportation is trying to replicate a quantum state which is present at one place, okay, and you try to replicate it into another place which is very far away from the original place. Now, note that this does not mean that you actually send the quantum state or quantum particle from here to there. So that is not allowed. But what instead you can do, you can follow a particular protocol, and that protocol typically depends, crucially depends on the presence of an entangled pair of objects. So somebody or some source in the middle generates an entangled pair of particles or objects and send one of them B to the original party, say Alice, located at one place, and the other particle C or the other quantum states goes to another party which can be located far away. Okay, in principle, it can be located anywhere. Now, what the first party does is to actually take this state, one part of this entangled pair, and then combine it with the original state he or she wants to teleport and make a measurement. And depending on the outcome of that measurement, send some data to his or her friend who is located far away. Now, this data is sent actually using any classical means. It can be fiber optics, it can be a telephone call, it can be free space communication, okay, using light as well. Now, depending on this data, depending on this message sent by this party's friend located far away, the final party applies some treatment on his part of the pair of entangled objects. And upon applying that treatment, what is the outcome? The outcome is an exact replica of the original state which the party here had. Okay. So this particle which is destroyed at the original party goes to the other party, right? So why do I say destroyed? Because in quantum mechanics, there is the famous no cloning theorem. You cannot clone or replicate the exact copy of any state. So this whole process of teleportation destroys the original state. So what is the upshot? The upshot is that you can recreate any quantum state at anywhere else in the universe. And this is not just science fiction. And today there are experiments in the world which say that teleportation is indeed possible from, say, places on the Earth to artificial satellites which go around the Earth. So far it is possible only using one or two photons, okay, microscopically, but in future, scientists are trying to extend it using a large collection of particles. So this is one example of a quantum task other than quantum computation. So we have so far learned of two tasks. One is quantum computation, the other is teleportation. Now let me also go to a very important third task, and that is called quantum key distribution, or using quantum mechanics to perform cryptography. Now, cryptography, all of you know, is to do with, generating some secret and sharing with some trusted party. For example, Alice can generate a secret key, and she wishes to share the secret key with her friend Bob, who may be located at some other place. Okay. But now there can be some eavesdropper, Eve, who can try to crack this key or hack this key. So all of you use passwords in your computer, and passwords are nothing but examples of a secret key. And passwords are based on combinations of characters and numerals on a keyboard. So you can see that if you have a keyboard, so you can make a password as complicated as possible. You can try to use more and more characters or numerals from your keyboard. But ultimately, you are limited by as many characters or numerals that are present on your keyboard, on your keyboard. Now think that somebody has a very powerful computer, so one can try to hack this password. So what one he or she has to do is just to run an algorithm, and the more powerful a computer is, the better chance of hacking this password, because after all, it is based on combinations of some finite elements. So in principle, all classical keys can be hacked. But in quantum mechanics, this privacy or secrecy, it is not founded on the fact that eavesdropping or hacking requires a very difficult computation, but it is founded on principles of fundamental physics. Okay. And what essentially happens there is that it is based on application of the uncertainty principle or uncertainty relation. And what does the uncertainty relation tell us? It tells us that if we want to gather information about a quantum state, we end up disturbing the state unavoidably. So if there is some Eve who is between these two parties who want to share some communication, Eve tries to intercept a message that Alice sends to Bob. Now, by her very process of interruption or extracting information from the state, Eve will unavoidably disturb the state. And once Eve does it, then Alice and Bob will know for certain. So the fact, again, what I want to emphasize, that privacy is founded on principles of fundamental physics like the uncertainty relation and no cloning theorem. So this much about three very prototypical tasks of quantum information processing, right? So now these tasks, as I said, are based on certain quantum resources or quantum principles, which we want to discuss in this talk now. And what basically we mean by quantum resource is that any property in quantum mechanics which helps us in achieving such quantum tasks, which I showed you, prototypical tasks which were originally formulated starting from 1980s onwards. Okay, and these tasks have today helped us in performing so many beautiful things that now this century is called the quantum century. That is why we are celebrating with much fanfare 100 years on quantum mechanics, and that is why all large technologies these days have to look an eye and keep an ear open on quantum technologies. Okay, so what are examples of quantum resources? So as I said, one of them I already discussed. Entanglement is a resource which it helps us in achieving quantum teleportation, for example. Okay, so I'm just giving you examples of such resources. There are many, many, many more examples. Next, I would highlight the resource of quantum coherence. And basically, in this case, by coherence, I mean not very different from quantum superposition that you learn in your basic school in quantum physics. And quantum superposition helps us in doing quantum computing, as I showed in the one of my very initial slides as well. So next resource one can think of is something called quantum non-locality, which some of you may have come across in the school itself by from Professor Aditi Sen's lecture. And quantum non-locality actually helps us in device-independent certification of entanglement. Also, it is very helpful in quantum cryptography, device-independent quantum cryptography. Now, these three examples I've given you have to do with spatial correlations in quantum theory, superposition, entanglement, so on and so forth. But there are also certain other types of correlations which are called temporal correlations. And temporal correlations are also a quantum resource, and they can play a big part in security. And sometimes such temporal correlations are easier to achieve and preserve than spatial correlations. In addition to such correlations or such resources, there are also other types of resources. For example, by the very nature of measurements in quantum theory. So whenever you talk of measurements, you talk of measurements using quantum mechanical laws. And again, due to the uncertainty principle, you know that certain measurements in quantum mechanics are incompatible by the very nature of the quantum theory. And such nature of measurements can also act as resource in quantum information processing. And finally, towards the end of this talk, I would also like to highlight another very beautiful property of quantum mechanics, which is called quantum contextuality. And this can also play a very useful role in quantum computing. And if time permits, I would also like to just mention for you that even our environment, and which is not quantum, which is taken to be classical, its action can also help in certain processes like quantum memory, which in turn can enable us to perform beautiful tasks using quantum resources. Okay. So now, after this introduction, let me again try to remind you what is the perspective of today's talk. The perspective of today's talk is essentially quantum resources and how to detect them. Okay, so the most important is it is not enough just to talk of quantum resources, but when you have to apply them in practical scenarios, you have to know how to detect such quantum resources. Okay, so what we will give or we will do in this talk is to consider the examples of some quantum resources. Some of them I've already talked of, and then we will try to show how such resources can be detected or certified. Okay, in other words, we will present schemes which are quantum mechanically valid for detection or certification of such resources, and these schemes have to be practical. Okay, and therefore one needs to assume minimal. Okay, one needs to use minimal assumptions and costs for implementing such resources. So by the way, so I would like to interrupt myself here and go to the audience and see if there are any pressing questions or clarifications at this time. So do you have any pressing questions or clarifications? Anybody in the audience? Of course, so far it is just the introduction. But I would like to also tell you that at any stage of the talk, if you have any pressing questions or comments, you can please interrupt me and you can ask it, because the purpose of this talk is not to just say, I mean, not to just give a monologue, but and not to just complete what all I have in my slides, but to make my message come across to you, the audience. So again, if you have any pressing questions or comments, you are just welcome to interrupt. Okay, so let me go back to my slideshow. Okay, so let me go back to my slideshow. Okay, so now let me just begin with, since quantum entanglement is one resource which is quite ubiquitous, let me again just very briefly introduce you to what is quantum entanglement. Well, quantum entanglement is relevant for composite quantum systems like this. Okay, psi, it is a composite system. It can be expressed as something which resides on individual Hilbert spaces of so many different parties. Now, suppose you have two entities A and B, so you can write a joint physical state psi A B. Now, an entangled system is such that if yes, anybody, yes. So I heard some noise. Anybody wants to say something? Okay, fine. So an entangled system is such that you cannot express your composite system wave function as a direct product of these individual wave functions. Okay. So this is a very simple definition, but it has a profound significance. And what is the profound significance? It tells us that individual description of either subsystem A or subsystem B have no meaning whatsoever. So whenever a system is entangled, one can only talk of joint properties of the total system. So this is a profound meaning to it, and this is something which is given the name of quantum non-locality. So example I can give you, you can think of a source which emits two particles. One goes to this side, the other goes to side B. And whenever you can write the total state as a combination of these states, which are functions of course the basic states, which cannot be expressed as a direct product. So for example, one may think of two spin half particles, okay, which I can express as up and down states by taking the Z basis. So I can write down four maximally entangled states, which are again the basic building blocks of quantum entanglement for qubits, and which are phi plus minus and psi plus minus states. Though these are also examples of maximally entangled states or bare states, which are used for as fundamental resources in information processing. And these states all of you have heard of even in your, say, condensed matter classes or optics classes, when you use, instead of spin half minus, you use photon polarization. Okay, vertical and horizontal polarization.
Professor Mazumdar,
Yes,
you are not audible properly.
I'm not audible
Yes,
properly.
yes, sir. You are properly audible now.
Now, am I properly audible now? Yes.
Yes, sir.
Yes, sir. You are properly audible now.
Okay, okay. So whenever I'm not, please tell me. Okay, I hope, yeah, I am. Okay. So now quantum entanglement, to repeat, I've given you an example with two basis vectors, and for example, spin of two electrons and polarization of two photons, but it is a general concept. And it means that two or more particles in quantum mechanics have the ability to acquire certain correlations. And by correlations, what I mean is as follows. If you consider this state, the example I've written here, so for example, the state is shared by two parties, Alice and Bob. And if Alice measured, say, along some previously chosen basis, say Z basis, and gets the zero outcome or upspin, then if Bob measures on his particle, he is bound to get the one outcome or downspin. On the other hand, if Alice measures and gets the downspin or labeled by 1, because Bob, when he performs the measurement, he is bound to get 0 or upspin. So then this means that the particles which Alice and Bob are sharing are correlated in their properties, and in this case particularly their spin eigenvalues. Okay. Now, the ability of two particles to acquire such correlations and also retain them, correlations in physical properties, even when they move far away from each other. This ability is called a resource, and such an ability is used for performing beautiful task in information processing. Okay. So now let me give you a mathematical definition of pure states, entanglement in pure states. So if you have n basis vector moving away from just say two basis vector or spin of states, you can express your state like this, okay, where you are the complete set of basis vectors, and you have to normalize your state like this. Now a pure state chi in this product Hilbert space is called separable if and only if it can be written as a Kronecker product of such states. Okay, psi which belong to Hn and phi which belong to Hm. Okay, so initially these two Hilbert spaces can have different dimensions such that chi is a direct product of psi and phi. Otherwise, this chi is entangled. So this is a general definition for pure states. Now, an example for pure states, this is the most basic example, okay, which I've written here. So this is the psi plus state, one of the four possible Bell states in 2 cross 2 dimensional Hilbert spaces, okay. And let us take this phi as again alpha 0 plus beta 1 and phi 2 as gamma 0 plus delta 1 when all these are also normalized. Now, suppose I don't believe, I don't agree that this forms a entangled state. I say that, let us say that this is separable. So the proof can be shown from contradiction. So then if it is separable, then I can express phi plus as a direct product of phi and phi 2, phi 1 and phi 2. And let me do exactly the same using this definition. So now I can, let me try to express 0, 0 plus 1, 1 as a direct product, and let me now open these brackets. So therefore I will get 4 terms. But now you can see, so in order for this state 0, 0 plus 1, 1 to be expressible exactly like this, the top line, I need to find examples of these coefficients alpha, gamma, beta and delta such that alpha gamma equal to 1 by root 2 equal to beta delta, and also the terms alpha delta and beta gamma have to vanish. But you can easily convince yourself there are no values, no examples of values of alpha, beta, gamma, and delta such that this is true. Hence, we reach a contradiction. Psi plus cannot be expressed as a direct product. So therefore, psi plus is indeed entangled. So now let me go to the entanglement of mixed states. So now if we consider a statistical mixture of pure states, that is how mixed states are described with some probabilities, then big states, by the way, do not possess any state vectors. They are described by density operators. So I can write down one such density operator like this. Okay. So Pi are the probabilities for obtaining these elements of this statistical mixture. Now, what is the definition of such? So let psi HA and HB be Hilbert spaces, and let me denote rho as a density operator of state from this product Hilbert space. Now, the operator rho is separable if there exists a sequence, okay, Pi I equal to 1 to n, of positive real numbers and which has to sum to 1 due to normalization, and a sequence of density operators rho I corresponding with states of HA and such, and rho IB which correspond to states of the other rho B, okay, such that rho is expressible like this: Pi rho I A tensor rho I B. And if such a mixed state can be written as a convex combination of Kronecker product of density operators as I've written, then this state is separable. If I'm unable to express this mixed state as such a Kronecker product, then this state is indeed not separable, or in other words, this state is entangled. So this is the generalization of the definition which we have used for pure state. Only in this case, we are using density operators instead of state vectors. Okay. So now this is a good definition, but then suppose you are given some state, then your task is very difficult to identify whether such state is pure or mixed. So we can try to think of an easier definition, and such easier definition was proposed by some founding fathers of quantum information, that is Perez and Horodecki, and this is called a positive partial transport criterion. Now, running through it very briefly, so how do you actually try to discriminate whether a state is pure or mixed? So you can express your, if you have pure states, then you can express it using the Schmidt decomposition. And a state, pure state, is separable only if it has a unique Schmidt coefficient, and that's lambda is equal to 1. Okay, so that is the definition of pure state. But what about mixed states? So in mixed states, for example, mixed states in 2 cross 2 or 2 cross 3 dimension, the PPT criterion is sufficient condition for separability. Now, what is the PPT criterion? Suppose you write down this state, this density operator in time in terms of some basis states. Okay. Okay. Now, such basic states, you have to apply a partial transposition among one of these parties. Suppose you take a bipartite basis, so you have to take a partial transposition on either Bob's or Alice's basic states. Okay, so suppose you take a partial transposition on Bob's states, then your state can be expressed as rho A tensor rho B partial transpose. And similarly, if you take a partial transposition rho A, then it can be expressed as rho A partial transposition tensor rho B. Now, a composite state in 2 cross 2 or 2 cross 3 dimensions is separable if and only if rho TA is positive definite. Okay, so density operator is positive. Then only then and only then the state is separable. Okay, so you can consider an example and it will be easier for you to find out. For example, if you consider this again, this pure state phi plus, you can express its density operator. It is very simple. It is an outer product. Now you take a partial transpose of one of these two parties. Okay, so let us say Bob's party. So therefore, only one of these is flipped. So this, in this case, half term turns out here. In this case, half is here. Now, if you try to calculate the eigenvalues, you can write the spectrum. The spectrum is such that one of these eigenvalues is negative. So one eigenvalue is smaller than 0. So therefore, rho TB is not positive at all. And that means rho is entangled. Okay. So now let us come to the useful example, and that is the example of a Werner state, which is the mixed state. So this is an n cross n dimensional bipartite state, which is invariant under unitary u cross u for any unitary. And as an example, I can consider a pair of, say, spin-off particles, which is a singlet, but which is an impure singlet. Okay. And what do I mean as an impure singlet? I can take a combination of this singlet state and combine it with a perfectly random state, which is represented by identity. And I can say in my combination, X fraction is in the singlet part and the remaining fraction is in the identity. So this is an example of a well-known Werner state in 2 cross 2. Okay. Now for this Werner state, I can take again a transpose on one of these two parties of this bipartite, and you can usually do the math. If you can take a transpose, you will get this state from here. Now you can compute your eigenvalues, and you can see these are the 4 eigenvalues. Okay. Now by definition, I have taken X to be positive, ranging from 0 to 1. Now you can see here that one of these eigenvalues can be negative only if your X is greater than 1 by 3, greater than or equal to 1 by 3. On the other hand, it is positive definite for X less than 1 by 3. So now from the definition of PPT, Werner state is separable for X less than 1 by 3. So this is the use of this PPT criteria. Okay. So now using these basic definitions, we will move to study our basic resources. So these definitions are very important. So I've spent the first half an hour, 40 minutes of this talk on basic introductions. So now I will try to discuss or describe such resources. Okay, so first resource I will consider as quantum entanglement, and entanglement is, again, to repeat, is a very useful resource for performing many tasks which are not achievable using classical physics, such as teleportation, superdense coding, cryptography, error correction, and some applications in quantum computation as well. Okay, then the question is that entanglement, it is very useful, but how does one verify or how does one detect quantum entanglement in the laboratory? Because after all, yes, I can hear some noise. So is there any question or so I don't hear any question. Anyway, let me ignore this noise. Let me proceed. So the
Miss
point is that
Deepshika, please. Miss Deepshika, please switch off your microphone. Madam Deepshika, I request the host to put her mic switch off.
yeah, thank you. So whenever you have any question, please switch on your mic, but otherwise, please keep it switched on off because there is too much noise. Anyway, so I always encourage interruption, but it has to be some coherent interruption, which will help all of us to progress in this topic. Okay. The question is that how does one detect entanglement in the lab? And in other words, typically in the lab, what happens is that you can prepare your states during some processes, and I can still hear some continuous noise, which is not good for the talk. So maybe let me keep quiet for a while, and could you please reduce the noise?
Madam Madam Diksha, please switch off your microphone. Madam Diksha, hello, Madam Diksha, please switch off your microphone. Madam Diksha, Madam Diksha, can you
I
hear me?
don't
Please
think
switch off your microphone.
I don't think the person is there sitting in front of the computer. So as a host, you have to switch them off because some people just want to switch on, or maybe because of some reason they have to go somewhere. So you have to, as a host, you have to switch it off.
Hello, host. Hello, host. Are you there?
I think host can mute everybody.
Yes, we are trying. Sorry for the inconvenience. Please bear with us. We are trying to put her microphone off.
पाय खाली करा पाय खाली करा नको नको मोशी इकडे
Hello, Professor Mazumdar, are you there?
Yes, I'm very much there. So if you
Uh,
have sorted out, then we can begin actually.
yes, sir. We are extremely sorry for the
No, no,
inconvenience.
no
You can
problem.
start.
No, no, no problem. These things can happen. Only thing that it is disturbing to carry on. No problem. It's not your fault. So people have to be more careful. But
could
no
you
problem.
yeah
So
Professor Mazumdar, I'm here.
yeah.
Vishwajit, could you put that person off?
No, ma'am, I am
Vishwajit,
not the host. Ma'am,
that's
only
fine,
host
but
can
I
put.
cannot. I know I cannot identify the person. Who is the person? I'm not finding out. That's why.
Her name. She put her mic already off, ma'am.
Okay,
Ma'am,
then
we have removed that person. We can
okay,
continue now.
okay. Thank you so much.
Okay, ma'am.
Okay. So in that case, I can resume. Right. So yeah, let me go back to the slide. Yeah. So slide show. Okay, so basically we are trying to actually describe what is entanglement, why is entanglement useful, and then the question we were posing is the following: that how does one detect entanglement in the lab? And the question is typically, as I was trying to say, that in a typical experiment, somebody prepares a quantum state, and then one wishes to know whether the state preparation is actually what we want. It is actually, I mean, correct. And in other words, will such a state be useful for information processing? And how do you actually check that? Because you cannot, once you prepare a state, all your calculations will not help you because you've already prepared the state. So you have to do something to the state, again, experimentally, in order to find out whether the state is useful or not. And what you exactly do is to you measure some operators on that state, which is a perfectly legible, legitimate procedure. And in quantum mechanics, you know that Hermitian operators are the one which will give you real eigenvalues. So you have to construct some Hermitian operators which are known as witnesses. Witnesses for what? Witnesses for checking whether your state will be useful for all the applications. The state you have prepared will be useful for all the applications that you want to use it for. And then you measure such an operator means that you measure the expectation value of that state, okay, of that operator in that given state, given unknown state, and using that you find out whether the state that somebody has prepared is entangled or not. So this is the formalism for entanglement witnesses. And then you have to also check whether this measurability is practical or not. Okay. So now, I mean, so this is a very important concept in the theory of quantum entanglement, and the fact that separable states form, all separable states form a convex states is what is a property in quantum mechanics that allows you to construct such witness operators. That means if you denote this blue picture, blue diagram or blue region as a set of all separable states, any state which does not lie here or which lies outside this, represented by the red region, is something which is separable, which can be separated from the set of separable states. Okay, and how can such states be separated? You can construct a sort of plane here. If you just imagine it to be a two-dimensional surface, this line you can imagine as a plane. By the way, this need not be two-dimensional. This is an arbitrary n-dimensional hypersurface. You can construct an arbitrary dimensional hyperplane, which can separate out this region, okay, which lies upwards or to the right of this plane from all separable states. And any state which belongs to this region, which is this side of this hyperplane, can be actually measured or detected by such a hyperplane. And what kind of hyperplane you need here? You need here is what is called an entanglement witness, which is a Hermitian operator in quantum mechanics. Okay. So this definition of an entanglement witness, W is an operator that is positive on all separable, that is if you're talking of two-dimensional two-party states, on all biseparable states. And if it is not, that is if trace of W, okay, on some state rho, that is the expectation value of W on some state rho, gives you a negative value, then it signals a entanglement for you. So this definition was proposed in the early 2000s or late 1990s by these people, Ordechi, Tarhal, Levenstein, Krausen, etc. So then you search for these such entanglement witnesses, and entanglement witnesses you try to find out using your operators, witness operators. Okay, so entanglement witnesses can detect all entangled states. Why? Because the set of separable states is convex. Only because the set of separable states is convex, you can actually, what you can do, you can actually denote or you can actually formulate such witnesses. Okay, but on the other hand, the set of all the separable states is not easily demarcated because the set of entangled states is not convex. Okay, so you cannot come down from the other side. That is the message. Okay, so now let us again take an example of such a bipartite separable state, which I can denote like this. And using the definition of mixed separable states, which I gave for you in one of my initial slides. Now you want to apply the PPT criterion, so you apply partial transposition, let us say, on the second system. Okay, and from this partial transposition, because it is separable, you get a positive partial transposition. So therefore, you actually see that these are demarcated by the PPT criteria. However, in general, there exist states which are entangled, as we have seen through examples also, and from such a PPT criterion, you do not get it. You do not get a partial transposition always to be positive. Okay, so therefore, using such PPT, we can construct entanglement witnesses, which is the simplest formalism that detects the entangled state psi, which is entangled. So you can construct a witness operator using such a definition, that is your transposition on one of these. Okay, let us say this V. Okay, so V is an eigenvector of psi T1. Okay, with the smallest eigenvalue. You can choose such an eigenvector which is smallest eigenvalue, which is negative. And why it will be able to detect entanglement? The proof is very simple. Since by definition this action on this psi will give you some lambda where lambda is less than 0. So therefore, the expectation value of this witness, which I have defined through these V's, will automatically be less than 0. And this is just using the cyclic property of this trace. So therefore, the witness is able to detect the state psi as entangled. But again, by its definition, again by the PPT criterion, for every separable state, rho W trace of this will give you greater than 0. So therefore, this is done. So you already have a witness which you have constructed. So let me repeat this definition. So let us denote sets as SCP and ENT for all separable states and entangled states respectively. If there exists a Hermitian operator which at least one negative eigenvalue, it can be called an entanglement witnesses provided two conditions are satisfied. One is that for all sigma which belongs to the set of separable states, you will have the expectation value as greater than equal to 0 of W, but there exists at least one entangled state, that is rho, which belongs to this set of entangled states, such that the expectation value of W returns a negative value. So therefore, a negative expectation value of a witness on a state indicates the presence of entanglement. Okay, so I can give you examples of such entanglement witnesses, but since we are running short of time, let me not go through these these examples. I will be sharing my PPT slides anyway. So those of you who are interested, you can look for these these witnesses. But let me come down now to one application of such witnesses. And this application of witnesses is in the theory of quantum teleportation, which I briefly introduced for you in one of the initial slides. Well, teleportation is not just by itself important, but it is also a very typical or prototypical general information processing task. Why? Because its utility is again immense in distributed quantum computation. So when someday you have practical quantum computers, not everybody will have large quantum computers, but you can have a network of small size quantum computers, and still you can achieve what you can achieve using a very large quantum computer. How you can actually talk among these smaller quantum computers using teleportation. That is the whole point. Okay. Now the teleportation theory is also well studied. For example, many years ago, say 10, 15, 20 years ago, people realized that not all entangled states are useful for teleportation. Okay, so it is not just enough to have entanglement in quantum theory, you need to have something more. And we also worked on it, 10, 15 years ago. So say again, giving an example of a mixed state where we showed that not all entangled mixed states are useful for quantum teleportation. So the question arises, so if you have an unknown state with you, how would you know that it is useful for teleportation? So again, we will apply the formulation of witnesses here, and for applying this witness in teleportation theory, we need to know some more about teleportation theory. And this is a mathematical property of teleportation theory, which is called the fully entangled fraction. Okay, so the task of teleportation, again to repeat, is to transfer an unknown state of a quantum system to a distant location, and this is achieved by a resource of an entangled state. Right. So the final result is the true copy of the original state, which is initially at A, is now transferred to B. The original state of A is destroyed, but the physical system S is not transported from A to B. Okay. So example, you can use an entangled with bipartite source maximally entangled state. So then Alice can share one particle from the state, and Alice can have initially this pure state, and using some procedure, some classical message, she can transfer to the party Bob, which is far away, and Bob, depending on Alice's message and his part of the entangled state, can exactly replicate the state. Okay, here, right? Okay. So this is teleportation, and you can achieve it practically using EPR state of entangled photons. That is very practical, and you can indeed achieve it. And you can achieve it at a far place. Like for example, you can achieve it from Earth to satellite or between two satellites also. Now the question is, the state that you are sharing, that you have prepared in your lab, will that state be useful for teleportation? How will we know? We will know from using our witness theory, right? So therefore, we construct this witness for teleportation, and this witness for teleportation is again constructed using the protocol that I state. So these are again the some mathematical aspects of the protocol, which perhaps I do not have time to go into, but you can look into this slide as well as my paper. So again, the question, the task is that you have to prove that the set in this case S of all states which are not useful for teleportation is convex and compact. So that is what we did. And so therefore, if you can prove it, so then any point or representing any state which is lying outside the state can be separated from it by a hyperplane. And therefore, the states outside is indeed used for teleportation. Okay. So this makes possible for Hermitian operators with at least one negative eigenvalue, which is able to distinguish such states, which is useful for teleportation. So this is the thematic schematic cartoon picture. These are sets which are not useful for teleportation. I can find the hyperplane, and corresponding to a hyperplane, I can find a witness operator which can detect such a state which is useful for teleportation. And this is indeed what we did in one work which is now 13 or 14 years old, and we proposed this theory for teleportation witnesses, and we measured that state. Okay, and the other beauty of this is that the expectation value is indeed performed is through measurable through local measurements, and this allows many applications. For example, I can give you an example of a paper which appeared almost 8 years after our papers, which uses this formalism for entanglement witness operator in quantum teleportation in a problem which is very different. Okay, which uses this in a boson sampling problem. Okay, the sampling problem which uses this method for quantum teleportation. Okay, so now before going on to the next final part of my talk, I would again like to kind of interrupt myself and try to ask you, is there any question? Is there any, do you have any question at the moment? Yes, anybody? So I don't see any questions. So let me just then do the next thing. So let me just break for 5 minutes. In the time, you can go through a recap of what I just said, and I will come back after 5 minutes. And then if you have any questions, we will continue, or we will continue with the last part of my talk in approximately I will start after 5 minutes, so I will still have about 20 minutes remaining. Okay, so I'm now breaking for 5 minutes, coming back after 5 minutes. Yeah. Yeah, find them. I'm back now. So again, let me ask you uh, if anybody has a question. Okay, if not, so in the last 15 to 20 minutes, let me just give you some other examples of resources. So as I said, the focus of this talk today is quantum resources and their detection. And so what we have talked of so far is I've tried to give you one example, the most famous example of a quantum resource, and that is quantum entanglement. And what are the very briefly? So this part of the talk, the last part will be less pedagogic. So I will try to convey some information to you, and those of you who are interested may look up at references. So quantum resources can be more general than entanglement. And how do you detect such resources? And those of you who have gone carefully through the earlier part of my talk have actually seen that you detect them using some measurements which are possible in quantum mechanics. And for a quantum systems, you do a lot of measurements and then you observe some statistics of those measurements. And then you can conclude whether you have a real resource with you. And for example, you can have something like quantum non-locality, which is described by the violation of Bell-type inequalities. And again, I think Professor Aditi Sende gave an introduction to you of what it exactly means by these types of inequalities. And the main impetus, the main advantage is that using violation of Bell-type inequalities, you can do something which is called device-independent certification. And I'm just coming to that in the next slide, and something which is called self-testing, and which allows you to have or implement device independent security. And by device independent means that these days everybody knows of hackers who are always trying to crack or getting through to our devices. So you can realize using mechanical principles, and it's a setup, a practical setup, when you no longer need even to trust your device. Okay, let any hacker come, but you don't care. Okay, so that is something. Sorry, again I've exited the slideshow. So let us, yeah. So that is something you can achieve through something which is called self-testing, and we can implement quantum security through self-testing. And what does self-testing mean? It means that we can verify quantum states, and also we can verify quantum measurements without even having direct access to the quantum systems. Okay, because why? These quantum systems can be prepared by some other person, and they can also be hacked by some other mischievous person. So it means self-testing means that you can certify quantum entanglement without actually trusting your quantum devices, or without even having direct access to your quantum devices. Okay, so how does it proceed? So again, it proceeds typically as follows. So if you have two parties A and B who are specially separated and they share an entangled state, and you need it because you want to do some quantum information processing applications, okay, like teleportation or distributed computation or quantum keys, I mean, sharing a secret message. And then using, you can know, and some third party here who wants to establish or certify that these two parties indeed share an entangled state. Then what does C have to do? C has to just ask some questions of this party. By questions, I mean perform some measurements, suggest some measurements, which can be performed by Alice, who can communicate back some results. Similarly, C can do the same thing with Bob. And following it, this procedure for many runs, C or Charlie can collect some measurement statistics. And based on these measurement statistics, Charlie can actually certify or verify that Alice and Bob indeed share a entangled state, okay, without any direct access or without keeping any trust on Alice and Bob separately. This is the procedure, and this self-testing has many applications, as I said, QKD, randomness generation, computation, so on and so forth. And one particular subclass of self-testing is one-sided device independence, where you can study, where you can trust one of your parties and this is typically enabled by something which is called quantum steering. Okay, so why do we need one-sided, or what is the advantage of one-sided? So as you know, in many realistic situations, one of the two parties can be trusted, whereas the other may be completely untrusted. For example, in the bank, you have a server which can be trusted in a safe location, but your client may not be trusted. Similarly, if there is a manufacturer of quantum devices who you can pay some money to buy this, but you cannot trust the manufacturer. Okay, so on and so forth. So there are many advantages of one-sided DST. Okay, and this protocol, as I said, is based on again some beautiful property which is called quantum steering. So just a minute to describe quantum steering. Actually, the history of this is very old. In fact, Erwin Schrödinger, way back in 1935-36, was actually trying to understand the famous EPR paper by Einstein, Podolsky, and Rosen, and he actually discovered or realized this message of the EPR paper, and he felt that this quantum theory allows a system to be steered or piloted into one or other type of a state at the experimenter's mercy. And he thought it to be very disturbing, because after all, I mean, in quantum mechanics, you cannot send any signal faster than light, but you can still share some non-local correlation. So this was the first use of this word quantum steering in the literature of quantum theory. Okay, so the steering is very old, but it has numerous applications which have been proposed in recent years. For example, I can give you an example of one of our works, which we did in collaboration with Professor Girish Agarwal, who is a noted international expert in quantum optics. And also coming down the years also to something more recent, in 2018, we proposed the first protocol for one-sided device independent self-testing for any pure 2-qubit state. And again, this was mostly done with the help of our past and present students and postdocs. So this protocol was the first protocol for one-sided device independent self-testing, and it was also experimentally realized in a lab in China with our collaborators in China, and they actually detected this resource of quantum steering using a linear optical setup. So this is something which is quite contemporary. However, now let me, the last part, move to other resources. Again, steering is based on entanglement. Let me move to some other resources which are not based on entanglement. Okay. So what are such resources which are not based on entanglement? Okay. So for example, in one of my slides, I mentioned that there could be, so all these things, entanglement, non-locality steering is based on spatial correlations which depend on two parties which are separated in space. But in quantum mechanics, there can be correlations which can build up between two parties who can be separated in time as well. For example, if there is only one particle, you can make a measurement at one particular time, and after some time, another person can come and make a measurement on the same particle. And they will be sharing some correlations which can be quantified using these famous inequalities, which was proposed by the Nobel laureate Anthony Leggett and his collaborator Garg. Okay, this is also quite old, but you can use such an inequality to certify temporal steering in the same way spatial steering is certified by using Bell-type inequalities. Okay, now let me go back, let me come down to a key question, a sort of question which we can ask from our study of quantum mechanics. So you have studied quantum mechanics, you know that it contains so many beautiful properties like superposition, entanglement, so on and so forth. But you can also just ask this question: is there one fundamental property or key feature in quantum mechanics that sets it distinctly apart from classical physics? Okay, if there is one such property, what is that property which allows you to perform such beautiful tasks which are also technologically revolutionary, like the so many tasks I have mentioned for you? Okay, so can you answer? So we can attempt to answer this, and if you can pinpoint one such property, it has to do with nothing but the character of quantum measurements. Okay, so why? For example, you can say that why have you not said entanglement? Okay, But let me tell you that entanglement is a very beautiful property, but you at least need two parties, two or more parties to achieve entanglement. For a given single party, there is nothing like entanglement, okay, because you need two parties which are separated in space. But I've just told you in my last slide, there are correlations like temporal correlations which are also useful. So, which is something which inside quantum mechanics, which is not just entanglement, but it has to do with the character of measurement, that is measurement incompatibility. So in a nutshell, just to recap what I've said, that though quantum entanglement is a powerful resource, there exists tasks like quantum computing, for example, which are some quantum computing protocols are not based on quantum entanglement, and there can be other communication tasks also like QKD, quantum key distribution without entanglement, in the prepare and measure scenario. And primary such example is the original protocol of Bennett and Brassard way back in 1984, which is the first quantum key distribution protocol, which relies not on entanglement, but it relies on superposition. Okay. So how is it implemented? So it is implemented by the particular typical property or character of quantum measurement. So this question again, what causes advantage in quantum tasks without entanglement, which is something which is called the character of quantum measurements or measurement incompatibility. And something else also, contextuality, which I will come to just in a couple of more minutes. Okay. So just about a couple of years ago, we showed in this work, again, this work is done with our present and past students and collaborators, and among them, Devashish Shah is now a faculty in ISR Trivandrum. Devarshi Das is a Cambridge Newton Fellow. Bihalan has also moved to a postdoc position in Europe. Arun is still with me, he is completing his PhD. So what we showed that if you have any measurement incompatibility, if you have a set of measurements which can display such measurement incompatibility arising again from the fundamental uncertainty principle, then in such a situation, you can show that such measurement incompatibility can act as a resource for quantum communication tasks. So any generic quantum communication can be built up through this measurement incompatibility. And in this case, you do not need to rely on any entanglement. Okay, so this is one thing. So now in the very last part of my talk, I would focus more on such quantum tasks without entanglement. And in this case, I would like to highlight the role of contextuality, or typically quantum contextuality is its utility as a resource. Okay, so by the way, let me just go back to you and again give you an example. So this talk had a title of quantum computation, and indeed about 10 or so many years ago, there was an article in Nature by this group of Mark Howard, which came with such a title. This is a Nature paper, by the way. It says that contextuality supplies the magic for quantum computation. That means if quantum computation relies on something, what it relies on? It relies on contextuality. If there is something quote unquote magical in popular language, which is happening in quantum computation, it is nothing but the realization or effect of quantum contextuality. Okay, so let me come to what do we mean by quantum contextuality or contextuality in general. Well, in physics, among all your natural properties, you can classify them in two categories. So one is an attributive property, and which is something which is a constant property of an object, which you can measure and observe at any time, and such a property or attributive property is not modified by the act of measurement. For example, for a fundamental particle, you can think of its rest mass or something like its electric charge. Such a property is an attributive property of that particular fundamental particle, and you cannot modify it using your measurement, right? On the other hand, there is another kind of fundamental property which is called a contextual property, and such a property is revealed only in specific experiments or only under particular conditions. And such a contextual property actually characterizes the interaction of the particular object that you're measuring with the external world, and typically in this case a measuring operator. Okay. So for fundamental particles, you can think of properties like spin projection along a particular direction or axis or probability. Even in the classical sense, you can have a generalization. For example, a weight of a object or of a color of a chameleon. So in classical mechanics, also you can think of contextuality, but we will here restrict ourselves only to quantum contextuality. And why is probability that you measure in a random experiment contextual? Because probability is neither a property exclusively. Suppose you talk of a coin tossing experiment, then this probability of whether you obtain head or tail is not an exclusive property of the flipping device. Okay. So you can say that it arises from a combination of your original coin, whether it was originally in a particular state or its character, okay, whether it is weighted, biased or not, and then the action of a flipping device entails you that you get an outcome head or tail. So therefore it is a contextual property, this probability of whether you get a head or tail. Okay, so you can define experimental contexts in quantum mechanics, and this experimental context is set by the wave function or quantum state, and also the observable that you measure, which is an Hermitian or self-adjoint operator. And this typically depends on your experimental setup on how you measure this observable. So in quantum mechanics, you have this beautiful property of contextuality. And again, due to lack of time, because I am reaching the very end of my allotted time, such contextuality, the simplest example which was historically noted was by something called the Perez-Mermin square, which tells you, so you can, again, when I give you these slides, you can go through these mathematics and you can see for yourself that these three measurements define a context for you. And by the way, in quantum mechanics, you can realize this sort of contextuality only for dimension 3 and higher. You cannot realize such a contextuality in lower than dimension 3. So for example, in a state of qubits, you can realize, okay. So now quantum contextuality in practice is again obtainable for many different scenarios. You can also define contextuality for witnesses, which these people did, okay, way back in 28. And again, let me not go through these slides. So let me come finally to some applications of quantum contextuality without entanglement. As I can say, the many applications: quantum state discrimination, self-testing, computation, this Nature paper, QKD, quantum key distribution, so on and so forth. And finally, our work, this is also a work a couple of years ago. We formulated a contextuality experiment involving measurement of contextuality witnesses. And this work was published in PRL a couple of years ago. What we again showed that something which is again very fundamental, quantum contextuality actually not only drives communication, but it says why quantum communication is more advantageous than classical communication. And the more complicated, more, collective system you have, you enjoy more the advantage, and that is nothing but communication complexity. And indeed, such communication complexity advantage is obtained by quantum contextuality. Okay, so this is again used in many other resources. For example, let me not again go through these slides. That is something Wigner negativity. And finally, one last slide, that is in certain sense the role of environment, which can also help you with information processing. So all these papers, if you're interested, can have a look. So environment can help you with quantum memory, and typical of that is non-Markovian influence, which helps us in information backflow from the environment. And you can actually build up a resource theory for such non-Markovianity, and you can apply this such non-Markovianity for detecting such resources. So finally, I am at the end of my talk. So let me summarize. So what I have tried to convey to you here. So we have basically discussed quantum information processing broadly, including quantum communication and computation with quantum resources, and detection of such resources with something which is likely not only to lead to new insights on the fundamental nature of quantum theory, but it will light up our road to new technology. And again, to summarize, what are quantum resources? These are nothing but the possibility of performing new and interesting tasks through the use of quantum entanglement, well-known locality, steering, contextuality, so on and so forth. So detection is very important. And in this talk, I've tried to give you examples. Mostly I've discussed witnesses, but I've just mentioned that there can be detection schemes for other resources, for example, device independent certification, self-testing, temporal correlations, non-Markovian environment, so on and so forth, and which allows you to perform so many beautiful tasks like teleportation, and indeed other resources like measurement, incompatibility, and quantum memory. And the future prospect of this field is very vast. So we can actually indeed, on the way to technology, have to deal with multipartite correlations, large objects, high dimensional systems, so on and so forth. So I thank you for your attention, and any questions are welcome. Thank you so much.
Thank you, Professor Mazumdar, for your insightful and detailed lecture on quantum resources like entanglement and its various detection techniques.